Let me begin with a prediction. The aliens are probably not coming. Not tomorrow. Not next year. Probably not during the lifetime of our civilization. And I do not say that because I believe extraterrestrial life is impossible. Quite the opposite. The universe contains so many stars, so many planets, so many opportunities for chemistry to become biology, that it would be intellectually reckless to assume Earth is the only place where life has ever appeared. They may exist. They may have existed for millions of years. They may be looking at their own night sky right now and asking the same question we ask. Where is everybody? But existing somewhere in the universe and arriving on Earth are two completely different problems. Hollywood treats interstellar space as though it were an ocean. Build a sufficiently powerful ship, pack enough supplies, choose a destination, and begin the voyage. The engine roars, the stars become streaks, and after a short dramatic sequence, you arrive at another world. The real universe is not arranged that way. The great obstacle is not that our engines are too primitive. The obstacle is that space is offensively, almost maliciously large. The nearest star beyond our sun is Proxima Centauri, a little more than 4 light years away. People hear 4 and think the number sounds manageable. 4 blocks, 4 hours, 4 days, perhaps 4 years if the traffic is particularly bad. But a light year is not a unit of time. It is a unit of distance. It is the distance light travels in 1 year while moving at about 300,000 kilometers every second. In 1 second, light could travel around Earth more than 7 times. In 1 year, it travels nearly 10 trillion kilometers. Proxima Centauri is more than 4 of those years away. The nearest star is roughly 40 trillion kilometers from us. That is the nearest one, not the center of the galaxy, not a promising Earth-like planet selected by an advanced civilization, not a mysterious radio source on the other side of the Milky Way. The closest star, human beings have produced spacecraft capable of astonishing speeds. The Parker Solar Probe has moved faster than any other human-made object, reaching speeds of hundreds of thousands of kilometers per hour during its close approaches to the Sunday. That is an extraordinary engineering accomplishment. At those speeds, however, a journey to Proxima Centauri would still require thousands of years. And Parker Solar Probe does not travel at that speed because it has a science fiction engine. It achieves those velocities by falling deep into the sun's gravitational field. It is not a starship capable of selecting a destination and cruising across interstellar space. Even under an absurdly generous assumption in which we could simply aim it toward Proxima Centauri at its greatest speed, the journey would last longer than recorded human history. Imagine launching a spacecraft before the first cities were built, before the pyramids, before writing, before agriculture had transformed most human societies. Then imagine waiting until today and discovering that your ship had not yet arrived. That is the nearest star. The Milky Way is about 100,000 light years across. So when a movie shows aliens traveling from another region of our galaxy, the screenwriters are not ignoring a small inconvenience. They are ignoring a distance so large that ordinary human intuition collapses beneath it. The galaxy is not an enormous city. It is an enormous desert where the grains of sand are separated by trillions of kilometers, and the desert itself takes light 100,000 years to cross. You may say that our spacecraft are primitive. Give another civilization 1,000,000 years, and perhaps they will invent better engines. Of course, they would invent better engines. They might use forms of propulsion we have not yet built. Fusion engines, antimatter propulsion, laser-driven sails, technologies we have not imagined. But there is a difference between an engineering problem and a law of nature. Engineering problems ask, how do we build it? Laws of nature sometimes answer, you do not. Special relativity places a speed limit on anything carrying mass. As an object accelerates closer to the speed of light, the energy required to accelerate it further rises dramatically. You can reach half the speed of light. In principle, you can reach 90%. You might reach 99% if you possess extraordinary quantities of energy and solve problems that currently make our most ambitious missions look like toys. But you cannot accelerate an object with mass to exactly the speed of light. The required energy grows without limit, not merely an inconvenient amount, not the output of 10 stars, not the output of a galaxy, without limit. A sufficiently advanced civilization does not receive an exemption from mathematics. Technology allows you to explore what the laws of physics permit. It does not allow you to vote the laws of physics out of office. Now, relativity appears to offer a loophole. The faster you travel, the more slowly time passes for you relative to people who remain behind. This is called time dilation, and it is not a philosophical possibility. We measure relativistic effects. We account for them in technologies such as satellite navigation. So imagine a spacecraft traveling extraordinarily close to the speed of light. From the perspective of the people aboard, a voyage across thousands of light years might feel much shorter than the distance suggests. That sounds like the solution. It is not. It solves one clock while leaving every other problem untouched. Suppose the travelers experience only a few years during the voyage. Thousands or tens of thousands of years may still pass at the destination and at the civilization they left behind. They arrive at Earth expecting to meet the society that sent the signal they detected. But the signal was already thousands of years old when they received it. Then their journey required thousands more years from our perspective. By the time they arrive, the society they came to investigate may be gone. Its languages may be extinct. Its cities may be buried. Its species may have changed. The aliens would not be conducting diplomacy. They would be conducting archaeology. And if they intended to return home with a report, the situation becomes even more absurd. By the time the scouts return, their original civilization could be separated from them by longer than the entire history of Homo sapiens. Imagine asking a government to fund a mission whose results will arrive after the nation, language, culture, institutions, and possibly species that launched it have disappeared. Human institutions struggle to maintain a project for several decades. A serious interstellar mission could demand continuity for millennia. The difficult part may not be building the engine. The difficult part may be building a civilization capable of remembering why the ship was launched. And we have not yet discussed energy. Moving a grain of dust close to the speed of light is one problem. Moving a spacecraft is another. A real vessel requires structure, engines, communication systems, shielding, navigation, redundancy, possibly life support, and some mechanism for slowing down at the destination. People often calculate only the energy required to accelerate. But arrival is not accomplished by flying through the destination at nearly the speed of light. You have to decelerate. Whatever energy and engineering challenge you faced while gaining speed returns while losing it. A ship that cannot stop is not an interstellar visitor. It is an extremely expensive projectile, and space is not empty. This is one of the universe's crueler jokes. Interstellar space appears empty when viewed at human scales. The density of matter between stars can be extremely low. There are scattered hydrogen atoms, grains of dust, energetic particles, magnetic fields, and radiation. At the speed of an ordinary spacecraft, much of this material is manageable. At relativistic speed, it becomes terrifying. Energy depends on velocity. A tiny particle that would be harmless at low speed can release enormous energy when it collides with a spacecraft moving close to the speed of light. A grain of interstellar dust becomes something closer to an explosive. A hydrogen atom becomes high energy radiation. The faster you move, the more the universe in front of you transforms into a particle beam aimed directly at your ship. Your protective shield adds mass. More mass requires more energy to accelerate. More energy creates greater engineering demands. Greater velocity increases the danger of collisions, so you require more shielding, which adds more mass. The universe has now placed you inside an engineering feedback loop. You could try placing a massive shield in front of the spacecraft. You could attempt to use magnetic fields or plasma to deflect charged particles. Perhaps an advanced civilization would invent a clever solution, but clever does not mean free. every solution consumes mass, power, and complexity. And a system traveling for thousands of years must remain reliable across periods longer than any machine humans have ever operated. One broken component cannot simply be replaced at the next service station. There are no service stations. There is no rescue vessel. There is no nearby planet where the crew can purchase a replacement fusion regulator and continue the mission. Interstellar space is not merely distant, it is unforgiving. This is why alien invasion stories amuse me. The aliens somehow solve propulsion, energy, shielding, navigation, life support, time dilation, deceleration, and institutional continuity. Then they arrive on Earth and are defeated because someone uploads a computer virus, or because water exists, or because a human delivers an inspirational speech. If a civilization can cross interstellar space with a fleet of massive ships, we should not assume their greatest vulnerability is an outdated laptop. But perhaps they do not send biological beings, perhaps they send robots. Now the conversation becomes more interesting. Machines do not require oxygen. They do not become lonely. They do not need food. They can tolerate acceleration that would kill a human body. They might place themselves into low power states for centuries. They could repair themselves. Eventually, a sufficiently advanced machine might reproduce. This leads to one of the most unsettling ideas connected to the Fermi paradox, the self-replicating interstellar probe. Imagine a civilization builds one robotic spacecraft. The machine travels to another star system. It finds asteroids, metals, energy sources, and other raw materials. It builds copies of itself. Those copies travel to neighboring stars. One becomes two. Two become four. Four become eight. The expansion is not fast in the ordinary sense. Each voyage may require hundreds or thousands of years. Each system may require additional time for mining and manufacturing. But exponential growth does not need to be fast to become enormous. It only needs to continue. Depending on the assumed speed and replication time, a network of self-replicating probes could spread through the Milky Way in tens or hundreds of millions of years. That sounds like a long time. The galaxy is more than 10 billion years old. Earth is about 4.5 billion years old. On cosmic timescales, 100 million years is not an eternity, it is an episode. If even one civilization had developed self-replicating probes early in the history of the galaxy, and if those probes continued operating, the Milky Way could already contain their descendants. They would not need to invade. They would not need giant ships hovering above our cities. A small automated observer could be sitting on an asteroid. It could be buried beneath the surface of the moon. It could be drifting beyond Neptune. It could be the size of a refrigerator, a basketball, or an insect. We have not examined every asteroid. We have not mapped every cave on the moon. We have not searched every dark corner of the solar system for technology designed not to attract attention. So the absence of obvious alien machinery does not prove that no machinery exists. But the silence still demands an explanation. Maybe no civilization has developed self-replicating probes. Maybe civilizations routinely destroy themselves before reaching that stage. Maybe they reach the stage and decide that filling the galaxy with machines is irresponsible. That would be a comforting thought. Intelligence becomes wiser as it becomes more powerful. History does not yet provide overwhelming evidence for that assumption. Maybe advanced civilizations turn inward. They invest in virtual environments, computation, biology, or forms of existence that consume less energy and occupy less space. Maybe exploration is a youthful phase. Human civilization has already demonstrated how quickly institutional ambition can change. We sent people to the moon, then stopped. We did not lose the laws of physics. We lost the political and economic will to continue in the same way. A technological capability does not guarantee permanent motivation. The fact that a civilization can build something does not mean it will build it forever. Perhaps the period during which a society is both capable of launching interstellar probes and interested in launching them is surprisingly short. Or perhaps the great filter is still ahead of us. The great filter is the possibility that somewhere between lifeless chemistry and a galaxy-spanning civilization lies a barrier that almost no world crosses. Maybe the barrier is the origin of life. Perhaps chemistry rarely organizes itself into self-replicating biology. Maybe life begins easily, but complex cells are extremely rare. Life appeared relatively early in Earth's history. But for most of Earth's existence, life remained microscopic. The transition to complex cells appears to have been a profound event. Multicellular organisms arrived much later. Large brains arrived later, still. Technological civilization appeared only in the final instant of the cosmic calendar. Perhaps microbial life is common, but intelligence is rare. You could have a galaxy filled with oceans, algae, microbes, and strange chemical ecosystems, yet no one anywhere building a radio telescope. A bacterium and a civilization are both alive. They are not remotely the same cosmic event. Finding microbes on Mars would be one of the greatest discoveries in human history. If those microbes represented an independent origin of life, we would have evidence that biology can emerge more than once within a single solar system. That would suggest the universe may be rich with life, but it would tell us little about minds. Life on Earth needed billions of years to produce a species capable of asking whether life exists elsewhere. During those billions of years, Earth endured asteroid impacts, climate changes, mass extinctions, continental movement, genetic accidents, competition, cooperation, and countless events that could have unfolded differently. Evolution does not have a destination-marked intelligence. The dinosaurs ruled Earth for more than 150 million years and did not build radio telescopes. Intelligence is not guaranteed. Technology is not guaranteed. Survival is not guaranteed. Even if intelligence appears, a civilization must survive its own inventions. This may be the most dangerous stage. For most of human history, our ability to cause destruction was local. A conflict could devastate a village, a city, or an empire. Now we possess technologies capable of altering the entire planet. Nuclear weapons, industrial climate change, engineered pathogens, artificial intelligence systems whose future effects remain uncertain. Global networks capable of spreading information, misinformation, fear, and conflict at the speed of light. Our technological power has become planetary. Our emotional instincts remain tribal. That is not an encouraging combination. Perhaps many civilizations reach this point and fail. They learn to split the atom before learning to share a world. They create machines capable of transforming their societies before developing institutions capable of controlling the transformation. They become powerful faster than they become wise. The silence of the galaxy might be telling us something. Not necessarily that intelligence is rare. Possibly that technological adolescence is deadly, and we are currently inside it. We are not observing this experiment from a safe distance. We are the experiment. There is no control group. There is no more advanced civilization sending us instructions. There is no interstellar emergency service waiting to intervene when we make a mistake. If the universe contains ancient civilizations, their advice may be physically unable to reach us in time. If they sent a message 10,000 years ago, we might receive it tomorrow. If we answer immediately, our reply could arrive 10,000 years from now. Then their response would require another 10,000 years. This is not conversation in any human sense. You ask a question. Civilizations rise and fall. Languages are born and die. Continents shift, then an answer arrives. Imagine receiving a message from a society that transmitted it before the first human city existed. Are they still alive? Did they destroy themselves? Did they change into something no longer recognizable? Was the message sent by biology, machines, or a society that no longer distinguishes between the two? We would not know. Detecting an extraterrestrial signal would transform humanity, but not in the way movies suggest. There would be no immediate meeting, no alien ambassador descending a ramp, no dramatic countdown. There would be years of verification. Is the signal artificial? Could it be interference? Does it repeat? Does it contain structure? Does it encode mathematics, images, chemistry, language, or nothing more than a beacon announcing that someone once existed. Scientists would argue, governments would react, religious traditions would interpret it, conspiracy theories would multiply, markets might move, philosophers would suddenly become extremely busy. And after all of that, humanity would have to decide whether to answer. Then we would wait, possibly for longer than our civilization has existed. This is one reason distance may solve much of the Fermi paradox without requiring everyone to be dead. Civilizations may be common in space, but separated in time. One appears, it broadcasts for 5,000 years. Then it disappears or stops transmitting. Another civilization emerges 20,000 years later around a star 30,000 light years away. Both existed in the same galaxy. They never had a chance to communicate. The Drake equation organizes the problem by asking about star formation, planets, habitable worlds, the emergence of life, intelligence, detectable technology, and the lifetime of communicating civilizations. Its most important term may be the last one. How long does a technological civilization remain detectable? 100 years? 10,000? 10 million? We do not know. Humanity has been producing strong radio emissions for only a tiny sliver of our species' history. Our communications are already changing. Some technologies leak less energy into space than older broadcasting systems. An advanced civilization might become quieter. It may communicate using focused beams we never intercept. It may use technologies we do not recognize. It may deliberately avoid broadcasting its location, or it may have stopped existing. The Fermi paradox asks why, if civilizations are common, we see no obvious evidence. But the question quietly assumes we know what evidence should look like. We search for radio signals because we invented radio. We look for industrial pollutants because we created industry. We look for giant structures because we understand large-scale engineering. But another civilization might leave signatures we have not learned to imagine. An ant crossing a computer chip does not recognize the internet. Its failure is not technological, it is conceptual. Perhaps we are surrounded by evidence and lack the category required to identify it. That possibility should keep us humble. But humility must work in both directions. We should not interpret every unexplained light as an alien spacecraft. Unidentified does not mean extraterrestrial. It means unidentified. A blurry image does not become evidence of visitors merely because the alternative explanation has not yet been established. The proper scientific response to uncertainty is not to fill the gap with your favorite answer. It is to remain uncertain. Alien visitation is an extraordinary claim. To accept it, we require evidence capable of surviving serious investigation. Not testimony alone, not a light in the sky, not a video showing an object whose distance, size, and speed cannot be measured. We need physical evidence, reproducible measurements, technology, materials, signals, or observations that cannot plausibly be explained through known natural or human causes. The universe may contain life. That does not mean every mystery is an alien. Now, let us return to wormholes. Because whenever I explain the distances, someone reaches into Einstein's equations and pulls out a shortcut. Wormholes are not pure fantasy. General relativity allows mathematical geometries that resemble tunnels, connecting distant regions of space-time. Instead of crossing the ordinary distance between two stars, you travel through a shorter path created by curved space-time. That sounds promising. The mathematics permits solutions resembling wormholes. The mathematics does not promise that nature builds stable, traversable versions large enough for spacecraft. Many wormhole models require negative energy or exotic conditions to prevent the tunnel from collapsing. Quantum physics can produce effects associated with negative energy density under highly restricted conditions. But the quantities are tiny, the configurations are delicate, and nothing about them suggests that constructing a starship-sized portal is merely a matter of building a larger laboratory. Even if a wormhole could be created, you would need to stabilize it. You would need to control where it connects. You would need to survive the gravitational and quantum effects around it. You would need to prevent it from becoming a time machine that violates causality. Physics becomes deeply suspicious whenever your travel plan allows effects to precede causes. The equations have a habit of generating instability precisely where science fiction becomes most convenient. There are also warp drive concepts in which a spacecraft does not move through space faster than light. Instead, space-time contracts in front of the vessel and expands behind it. Again, the mathematics contains interesting solutions. Again, the physical requirements involve exotic energy conditions, extreme quantities of energy, stability problems, and questions about how the configuration could be created or controlled. A mathematical solution is not automatically a machine. Mathematics can describe the interior of a black hole. That does not mean we can build one safely in a parking lot. Still, we should remain open to surprises. Our present theories are incomplete. General relativity describes gravity brilliantly. Quantum mechanics describes the microscopic world brilliantly. Yet in extreme environments, such as the centers of black holes or the earliest moments of the universe, the two frameworks do not fit together cleanly. A deeper theory of quantum gravity may change our understanding of space, time, information, and causality. Could it reveal a mechanism for interstellar travel that we have not imagined? Possibly. I cannot prove that every future theory will forbid every possible shortcut. Science should not pretend to know what it does not know. But possibility is not probability. Every serious proposal for faster-than-light travel currently encounters enormous theoretical and physical problems. So the burden of proof belongs to the person claiming the shortcut exists. You do not get to say future physics will solve it and then behave as though the solution has already arrived. Future physics might also reveal new restrictions. The universe has surprised us many times. It does not always surprise us in the direction we prefer. Now consider another limit: cosmic expansion. The universe is expanding, and that expansion is accelerating. Galaxies on sufficiently large scales are being carried away from one another as space itself expands. The farther a galaxy is, the faster its distance from us generally increases. This does not mean galaxies are locally flying through space faster than light in violation of relativity. It means the space between distant regions is stretching. At great enough distances, that expansion creates a cosmic horizon. There are regions from which signals emitted now will never reach us, no matter how long we wait. Their light cannot overcome the expansion of the space separating us. Those places are not merely inconveniently distant. They are causally inaccessible. There may be civilizations beyond that horizon. We could never learn that they exist. They could transmit continuously for billions of years, and none of their future signals would reach Earth. The observable universe is not the entire universe. It is the region from which information has had time and physical opportunity to reach us. There may be far more reality beyond it, but a reality that can never affect us cannot become part of our evidence. That should make the universe feel larger and lonelier at the same time. Imagine countless civilizations scattered through a cosmos so vast that most can never communicate. Each develops mathematics. Each studies stars. Each asks whether it is alone. Each listens, and each hears silence. Not because no one else is speaking, because the geometry of space-time prevents the voices from meeting. There is something almost tragic about that possibility. The same laws that allow stars to form, planets to orbit, chemistry to grow complex, and life to emerge, may also place every conscious species inside its own island of causality. The universe produces minds and then separates them. But perhaps loneliness is the wrong interpretation. We already have company. We have one another. Alien invasion stories often reveal more about human psychology than astrophysics. We want extraterrestrials to arrive because their arrival would answer a question that has haunted us for centuries. Are we significant? If they travel across the stars to visit us, even to destroy us, then at least we mattered enough to notice. Cosmic enemies are psychologically easier than cosmic silence. An enemy gives you purpose. Silence gives you responsibility. If no one is coming, no one is coming to save us either. No superior civilization will repair our climate. No alien council will eliminate nuclear weapons. No visitors will hand us a technology that solves hunger disease, energy, or political conflict. Those are human problems. The universe has placed them within human jurisdiction. And this is where the discussion becomes more important than whether a blurry object is a spacecraft. Suppose we are the only technological civilization in the Milky Way. Then the destruction of human civilization would not be merely a tragedy for our species. It would be the disappearance of the only known part of the galaxy capable of understanding the galaxy. 400 billion stars, and only one world where matter has learned to calculate the ages of those stars. Only one world where atoms have organized themselves into music, mathematics, medicine, telescopes, memory, and love. That would be an extraordinary responsibility. Now, suppose we are not alone. Suppose the galaxy contains thousands of civilizations, each trapped inside its own region of space-time. Our destruction would still erase something unique. Whatever lives elsewhere did not evolve through Earth's history. It did not survive our asteroid impacts. It did not share ancestry with our oceans, forests, dinosaurs, primates, and early humans. It does not possess our cultures, languages, art, mistakes, memories, or particular way of seeing the universe. Other intelligence would not make human consciousness replaceable. A second symphony does not make the first one disposable. Every form of consciousness may be a unique experiment performed by the cosmos, and ours is the only experiment we can currently protect. The atoms in your body came from stars. This is not poetry pretending to be science. The carbon, oxygen, nitrogen, calcium, and iron within you were produced through cosmic processes. Stars manufactured elements. Explosions scattered them. Gravity assembled new systems. Chemistry became biology. Biology became nervous systems. Nervous systems became minds capable of understanding stars. You are not separate from the universe looking outward. You are the universe looking at itself from one particular location. And now this universe-aware matter must decide whether to survive. That decision occurs through policies, institutions, education, cooperation, technology, and the choices of billions of people who rarely think of themselves as participants in a cosmic experiment. But that is what we are. We are testing whether intelligence can become powerful without destroying itself. We are testing whether short-lived organisms can plan across centuries. We are testing whether tribes can recognize planetary problems. We are testing whether knowledge can grow faster than wisdom without producing catastrophe. The experiment is running now. There is no reset button. There is no second Earth waiting nearby. Mars is not an emergency replacement planet. No alien ship is hovering beyond the moon, prepared to evacuate the survivors. This world is where the known story of consciousness is happening. Protecting it should not require believing we are cosmically chosen. It requires understanding that we are cosmically vulnerable. Perhaps tomorrow, a radio telescope detects an unmistakably artificial signal. I would celebrate that discovery. I would want every instrument on Earth turned toward it. I would want independent confirmation. I would want scientists from every country involved. It could transform biology, astronomy, philosophy, religion, and our understanding of our place in the cosmos. But even then, we would still have to take care of ourselves. The signal might be 20,000 years old. The senders might be gone. They might never receive our answer. The discovery would give us knowledge. It would not give us rescue. So I do not find the cosmic silence entirely depressing. I find it clarifying. It removes the fantasy that our future will be delivered from outside. It tells us that what happens next depends on what we do here. Maybe microbial life fills the galaxy. Maybe intelligence exists around thousands of stars. Maybe we are alone. Every possibility leads to the same practical conclusion. Human civilization is worth protecting. If life is common but intelligence is rare, we are precious. If intelligence is common but contact is impossible, we are still responsible for our own region of consciousness. If we are entirely alone, the weight becomes almost unbearable. And if aliens are somehow traveling toward us, despite every obstacle I have described, then worrying about them today will not solve the problems already visible on Earth. The correct question is not when will they arrive? The correct question is, can we remain alive, curious, and technologically capable long enough to discover the truth? Can we survive the century? Can we preserve scientific institutions? Can we resist the temptation to turn every fact into a political weapon? Can we manage technology whose consequences extend beyond the people who created it? Can we protect the planet that supports every human argument, every human economy, and every human dream? Can we become a civilization that deserves to last for 10,000 years? Because 10,000 years is still almost nothing to the galaxy. We are impressed by a civilization lasting 5 centuries. Interstellar projects demand time horizons larger than the entire history of nations. Perhaps the real reason we see no galactic civilizations is that intelligence has difficulty maintaining purpose for long enough. Technology can expand quickly. Civilizational maturity may not. A species discovers radio, then nuclear weapons, then artificial intelligence, then biotechnology. Each invention increases its power before guaranteeing that its institutions can manage the consequences. Maybe the great filter is not a single catastrophe. Maybe it is the accumulation of short-term decisions. One election, one conflict, one neglected warning, one technology deployed before society understands it, one generation that assumes the next will repair the damage. Civilizations may not always end in spectacular explosions. They may simply become unable to continue the projects that once defined them. A starship does not require only an engine. It requires a culture capable of finishing what it begins. So when I say the aliens are probably not coming, I am not announcing that the universe is empty. I am saying that distance matters, energy matters, time matters, radiation matters, causality matters, civilizational endurance matters. The silence above us may be the combined result of all those constraints. Life could be everywhere and still never arrive. Intelligence could be abundant and still remain isolated. Signals could cross the galaxy while their creators disappear before receiving an answer. The universe can be crowded and lonely at the same time. That is the idea I want you to carry with you the next time you look at the night sky. Every point of light is not merely a star. It is a location separated from us by time. When you see a star 500 light years away, you are seeing it as it was 500 years ago. Any civilization observing Earth from that system sees our planet before modern industry, before radio, before airplanes, before anyone on Earth could announce our existence across space. An observer 65 million light years away, equipped with an impossible telescope, would see the age of the dinosaurs. Looking outward is looking backward. The sky is not a live broadcast. It is an archive. We inhabit a universe where distance and history are inseparable. That makes contact difficult in a way our stories rarely capture, but it makes astronomy beautiful. Every telescope is a time machine. Every photon carries an ancient report. We may never shake hands with another intelligence, but we can still learn about the conditions that made it possible. We can examine atmospheres of distant planets. We can search for oxygen, methane, industrial chemicals, unusual patterns of light, or artificial signals. We can explore Mars, Europa, Enceladus, Titan, and other worlds in our own solar system. We can investigate how life began on Earth. We can search the darkness without inventing answers. The search matters even if we find nothing. A null result is still information. If we examine thousands of planets and find no signs of life, the rarity of Earth becomes more apparent. If we find microbes everywhere, then biology may be a natural consequence of suitable chemistry. If we detect one artificial signal, the universe changes forever. Every outcome teaches us something. But we must survive long enough to conduct the experiment. That is the part no telescope can do for us. We built the telescope. We decide whether it remains funded. We decide whether children learn enough science to understand what it discovers. We decide whether civilization uses knowledge to expand perspective or to manufacture new methods of destruction. The Fermi paradox is usually expressed as a question about aliens. Where is everybody? I think the more urgent question is about us. How long will we be here? Will some future species on a distant planet receive a faint radio signal from Earth and realize that for a brief period, a technological civilization existed around our sun? Will they wonder what happened to us? Will our signals be all that remains? Or will humanity still be here, changed beyond recognition, wiser, more durable, and still looking outward? We cannot control the size of the galaxy. We cannot negotiate with the speed of light. We cannot stop cosmic expansion. But we can influence the lifetime term in our own version of the Drake equation. How long does our technological civilization last? That variable is not written in the stars. It is being written by us. So no, I do not lose sleep imagining alien warships entering Earth's atmosphere. I lose sleep considering the possibility that no one is coming, because everyone who might have come failed to survive long enough. I lose sleep considering that we may be approaching the same test. And I find hope in the fact that we can recognize the test. Awareness is not a guarantee, but it is a beginning. The dinosaurs could not calculate the orbit of the asteroid that ended their world. Microbes cannot measure atmospheric carbon dioxide. Most species cannot understand extinction. The universe has given us no promise of survival, but it has given us the ability to anticipate danger. What we do with that ability is the real story. Perhaps aliens will never visit us. Perhaps we will never visit them. Perhaps every civilization is confined to its own island of stars. Then let us make this island worth inhabiting. Let us become interesting enough, wise enough, curious enough, and durable enough that our brief appearance in cosmic history means something. Not because the universe assigned us a mission, because consciousness creates responsibility the moment it understands what can be lost. They may be out there. They may be listening. They may be gone. They may be separated from us forever. But we are here. For now, that is what we have. And the question of what we do with it belongs entirely to us.